Hi, good afternoon. My name is Andrew Paluch from Miami University, and so I wanted to share with you my presentation that I presented recently at the AIChE Spring meeting in New Orleans in the session on product and process design and development. So my presentation is on predicting phase behavior and intuitive solvent selection using MOSCED. So related to all the MOSCED work that I've conducted recently in my group here at Miami. Okay. And so when I received the call for papers for the session, the description read as such. Developing new products or processes involves multiple years of research and development. Any way to shorten this development activity will save significant resources to the company. For example, below are a few topics you can share with fellow members. Initial molecule selection from a pool of molecules, speeding up the development of process for new products with the help of computational tools or technologies, methods or tools to better estimate physical properties, and using chemical engineering principles to better assist with new product design or development. So when I read this call, I said, this is a perfect fit for my work on MOSCED, where we attempt to address all of these issues. Okay, and so I'd never presented at Spring before, but this seemed like the perfect opportunity. Okay, so over the last few years, we've published extensively on MOSCED, and so here's a selection of the papers that have been published so far. And so what I hope to talk about in this work is to give you an idea or an introduction of what MOSCED is and what its secret sauce is. Okay, and so my guess is most of the people listening to this or watching this screencast have never heard of MOSCED before. And that's okay. I hope to educate you in terms of what MOSCED is and what makes it special and why I get excited about it. And I'll also show you some example applications of the use of MOSCED for intuitive solvent selection. So the two examples we'll discuss in terms of entrainer selection and solubility enhancement. That work hasn't been published yet. It's in preparation, but will be available soon. But hopefully this will give you an idea of what's coming down the pipeline. If you have any questions about anything, if you want to send me emails, as soon as papers come out, you want copies or to keep updated, here is my email address. It's conveniently mosced@miamioh.edu. Please feel free to send me emails, or if there's screencasts you want in terms of better understanding MOSCED, reach out to me and I'll be happy to help you. My goal is to help. All right. So if you want to use MOSCED, I am here to help you. All right. So let's start out talking about MOSCED and its secret sauce. And so again, my assumption is that most people have never heard of MOSCED before. Right? You've probably heard about things like regular solution theory and Hildebrand solubility parameters, but not so much MOSCED. Okay. So first I want to try and tell you what MOSCED is, what makes it different from those methods I just mentioned, and what makes it special. Okay. And in terms of demonstrating, we're going to demonstrate with an example. Okay. So kind of the textbook example for maximum boiling azeotropes is the binary mixture of acetone chloroform. Okay. And so the general idea is acetone, all right, contains my carbonyl group. It is a great hydrogen bond acceptor. It's a great proton acceptor. Okay. Chloroform is a proton donor. All right. It has the CH group. Okay. So it can donate protons. Can also participate in halogen bonds, but those are going to be weaker than these proton donor acceptor relationships. Okay. So if I have a mixture of pure acetone, there's no real specific interactions for acetone with itself. If I have a mixture of pure chloroform, there's no real specific interactions for pure chloroform. Okay? But when I mix them, there's a propensity for acetone to associate with chloroform. Right? There's hydrogen bonding between chloroform and acetone. Right? I've even seen recent work out of Oak Ridge National Lab where they've demonstrated this using NMR. Okay. And so what I have plotted here on the left is PXY phase diagram. So vapor-liquid coexistence at constant temperature, isothermal VLE, for acetone chloroform at 323.15 Kelvin as predicted using Raoult's law. Okay. And what I get is this very skinny phase envelope. Okay. This being my bubble line up top and dew line on the bottom. On the right, what I have plotted as my straight lines is VLE as predicted using MOSCED. Okay. Circles being my experimental data. The important takeaway here is this dotted red line is my bubble line as predicted using Rayleigh law. In actuality, I have significant negative deviations from Rayleigh's law. Okay. So here's my expression for my bubble line. Okay. So my bubble line is x1 gamma 1 p1 sat plus x2 gamma 2 p2 sat. So in order to capture these negative deviations from Rayleigh's law, it must be that I have gammas less than 1. Right? I have favorable cross interactions leading to gammas less than 1. Okay. So if I want to be able to capture this association between acetone and chloroform, which leads to negative deviations from Rayleigh's law or gammas less than 1, okay, I need to be able to predict gammas less than 1. Okay, or equivalently, that'd be log gammas less than 0. Okay, so now let's talk about MOSCED. Okay, so my partial molar excess Gibbs free energy is equal to RT log gamma. And I can take my partial molar excess Gibbs free energy and write it in terms of a sum of my entropic and enthalpic contribution. Okay. Now, following the work of Abrams and Prosnitz and the development of uniquark, we could equivalently take this and write it as a sum of a combinatorial and a residual term. The general idea being my entropic term, right, or my combinatorial term, accounts for entropic effects. It accounts for size and shape assimilarities of my components in my mixture. And my residual term, right, is related to my enthalpic term and is related to intermolecular interactions. So I have a sum of a term that accounts for size and shape dissimilarities, and I have a term that results from intermolecular interactions. In MOSCED, we consider our limiting conditions. So we're going to consider or calculate limiting activities. So I write this as sum of my limiting combinatorial activity and sum of my limiting residual. Okay, and limiting, this is going to correspond to my largest or greatest possible deviation from ideality in that mixture. Okay, limiting activities are also nice in that it if I have a single solute in solution, right, this is focusing solely in on those very specific solute-solvent intermolecular interactions. All right, so now in terms of the combinatorial term, okay, what I've written down here is the combinatorial term, the limiting combinatorial term is given by Flory-Huggins expression, okay, log ratio of molar volumes plus 1 minus ratio of molar volumes. In MOSCED, we take the Flory-Huggins expression and we modify it slightly. We take our ratio of molar volumes and we raise it to this power AA2, okay, where AA2 is only a function of my solute descriptors. So AA2 is a function of tau2, alpha2, and beta2. This is my MOSCED or solubility parameter related to polar, and then hydrogen bond donated and accepting ability. Okay, but regardless, AA2 isn't some new adjustable constant. It's a function of my MOSCED parameters. And the purpose of AA2 is it's going to decrease, okay, this ratio of molar volumes for polar and associating molecules. Okay, so AA2 is going to be less than or equal to 0.953. The more polar or greater the association interactions in that pure solute, the smaller that value is going to be. Okay, but what's important is in general, my combinatorial term or my log of my combinatorial term is going to be less than or equal to 0. Okay, so my combinatorial term can account for negative deviations from Rayleigh's law, but on the last slide, okay, for acetone chloroform, we get negative deviations from Rayleigh's law, but they're going to be due to intermolecular interactions. Right? And intermolecular interactions are accounted for in my residual term, not in my combinatorial term. Okay. So with that, let's move on to the residual term, right? The term that's going to account for intermolecular interactions. Okay. So MOSCED is a solubility parameter-based method. Okay. So let's look at the two most popular solubility parameter-based methods out there. The first is regular solution theory. So in regular solution theory, my residual term is equal to V2, that's molar volume over RT, times difference in solubility parameter squared. Okay, where del 1 is my solubility parameter, it's equal to the square root of the cohesive energy density. Okay, but what's key is I have a difference in solubility parameters squared. So this term will always be positive, okay, and hence my residual term will always be positive. So regular solution theory is not able to get not able to capture negative deviations from Rayleigh's law due to intermolecular interactions due to my residual term. Okay. So regular solution theory then would not be able to capture that association effect in my binary mixture of acetone and chloroform. Okay. If I consider next Hansen solubility parameters, okay, so Pross is essentially paved the way of, okay, so here's, regular solution theory is great, but it has some limitations. And so one strategy to try and improve regular solution theory was to take my cohesive energy density, okay, so remember, del is going to be the square root of my cohesive energy density. So I'm going to take my cohesive energy density, and I'm going to write it as a sum of its individual contributions. So I'm going to write it as a sum of dispersion, polar, and hydrogen bonding contributions. Okay, and so what I've done here is I just have rewritten it in terms of parameters which we'll use in our MOSCED equation. I write it as a sum of dispersion, polar, and hydrogen bonding or association interactions. Where here, alpha is meant to indicate proton donating or hydrogen bond donating ability. Beta is proton accepting or hydrogen bond accepting ability. So my hydrogen bonding term is essentially related to my self-association interaction. Okay, this is the ability of component I to associate with itself. And so if I plug this in, then I get an expression for my log limiting residual contribution as V2 over RT, and then difference squared in dispersion, polar, and association interactions. And so what's key is these are all still differences squared. So this will result in a residual contribution that's greater than or equal to 0. So again, thinking back to acetone chloroform, we're going to get negative deviations from Rayleigh's law that result from association interactions between acetone and chloroform. Okay, since my negative deviations are resulting from intermolecular interactions, that should be accounted for in my residual term. Here, once again, I have a residual term that's going to be greater than 0. So Hansen is unable to account for this effective association between acetone and chloroform. Okay. And so that's essentially what's going to separate MOSCED from these two predecessors. Okay. So the general idea is, so Tishjin back in 1976 said, well, okay, one way, or proposed the idea in terms of accounting for these negative deviations from Rayleigh's law to essentially trying to account better for association. What he did is he took his residual term, my dispersion term's the same, my polar term's the same, and what he did though is he split my association term. He wrote it as a product of the difference in my hydrogen bond donating and accepting ability. So he took the association term and he split it up. Okay, and what this does for me is now it allows me to capture these negative deviations from Rayleigh's law due to association interactions. So the idea would be if in component 1, right? So if, component 1 has a big alpha and a small beta, and component 2 has a big beta but a small alpha, then component 1 would rather associate with component 2 rather than either component would with itself, right? It's able to account for this association interaction. And if we have association interactions like that, this term's going to work out to be negative. So if you have a case where alpha 2 is greater than alpha 1, while beta 2 is less than beta 1, then there's going to be a propensity for beta 2 to associate, or beta 2 to donate a proton that'll be accepted by component 1. Right? So there's going to be a driving force for association between those two components. They would rather associate with each other rather than interact with themselves. Okay? Or equivalently, if alpha 2 is less than alpha 1, while beta 2 is greater than beta 1, again, we have a propensity for the two components to associate. And if either of these situations is true, this term is going to be negative. Okay? And so what that allows us to do is we're able to capture negative deviations or negative contributions to our residual term and ultimately negative residual terms due to association interactions. Okay? So another way we can look at it that he put forth in one of our first JChem and data papers is if I were to take this term and expand it out, I could equivalently write it as negative 2 times mean cross interaction minus mean self interaction term. Okay, where cross interaction, this mean cross interaction, is just the molar average of my two possible cross interactions or cross association interactions, and then self being average of those two self interactions. So if my cross interactions are stronger than my self interactions, or my mean cross interactions or average cross interactions are greater than my average self interactions, then this term will be negative. So we'll get a negative contribution to my residual term, and we could ultimately get a negative residual term due to association interactions. So thinking back to that picture we started with, right, with these small modifications, we're able to capture negative deviations from Rayleigh's law due to association. Okay. So that was the expression put forth by Tisgen. So MOSCED, is a little different, right? And so essentially what we have is, compared to that Tisgen equation, right, I still have a different square root in my dispersion, different square root in polar, and then the same split in my association. Okay. But where MOSCED is a little different, or where it's kind of gone beyond that, is these superscript t's on my polar and association terms. That corresponds to, these are temperature-dependent parameters. So we have temperature-dependent solubility parameters, where MOSCED uses a simple power law type of scaling. Then in the denominator of my polar and association term, I'll see what are called asymmetry terms. Okay, and so the purpose of these asymmetry terms is my solubility parameters are solubility parameters. They're solute descriptors. Okay. So the general idea is the behavior of a component when it's a solute, infinitely dilute in a solvent, is different when it's the solvent with a solute infinitely dilute in it. So, behavior as a solute is different than behavior as a solvent. So these asymmetry terms are not adjustable parameters, but they are functions of my solvent parameters. Okay, so the idea is this is going to scale my polar and association term to account for the fact that component 1 is going to behave differently when it's a solvent rather than when it's a solute. Right? And I should point out in this expression, this is limiting activity coefficient of component 2. So component 2 is the solute, component 1 would therefore be the solvent. The other thing that's introduced is, in front of my polar term, I introduce this product of Q1 squared times Q2 squared. Okay, so this term here is meant to account for dipole-induced dipole interactions. Okay, and to give you kind of some insight in terms of the importance of these terms, when we've tried to do rigorous complete refittings, this makes a minor contribution. Right, and I should point out, in theory, you can think of Q's as being adjustable parameters, but there are heuristics. So if you have an alkane, Q is just set to 1. If it's an aromatic, it's 0.9. If you have an alkene, right, it's related to the degree of saturation or unsaturation. And only for specific cases is it really an adjustable parameter. Right, so there are some heuristics to getting it. But as I was saying, in the grand scheme of things, if you were to go back and refit everything, including Q, of course, makes your predictions better. You have an extra parameter in your expression, but it's not huge. Okay, the asymmetry terms though are very important. You can't exclude the asymmetry terms, refit all of our MOSCED parameters, and hope to get good quantitative predictions. All right, so these terms are actually quite important numerically. All right, so the last thing to kind of wrap up the state of art of MOSCED until we started playing with things is the original paper for MOSCED came out in 1984. Then in 2005, Eckert and co-workers tried to revamp MOSCED, and they revamped MOSCED by regressing parameters for 130 organic solvents plus water by fitting to 6,441 limiting activity coefficients. Okay, and what I take from the paper is they surveyed the literature and tried to filter out all of what they found to be accurate limiting activity coefficients, and using all available accurate limiting activity coefficients, these were the compounds they were able to regress parameters for. Okay, they also regressed parameters for 26 non-electrolyte solids using some solubility data, and there's some non-condensable gases and 1 or 2 ionic liquids in there as well. Okay, Okay? But, this is what I kind of see it as one of the main limitations of MOSCED is, this 2005 paper is very nice, but in the end, they're only able to regress parameters for 130 organic solvents. Okay, so it's great. We've have found it to be extremely accurate and is a wonderful model, but it's limited. So it's especially limited for design applications in that I'm restricted to just these 130 organic solvents. So we'll show at the tail end of this talk is we've spent a great deal of effort trying to expand the MOSCED database, making it more of a predictive tool in line with methods like UNIFAC. Okay. All right, so now if we get back to our original example, so again we had acetone chloroform, we had these negative deviations from Rayleigh law that resulted from association between acetone and chloroform. And so what I have here in this red box are MOSCED parameters for acetone and chloroform. Okay, and what I find is the situation of alpha of component 1 is less than alpha of component 2, while beta of component 1 is greater than beta of component 2. Okay, so there's going to be this propensity for association between acetone and chloroform. Right, acetone being the proton acceptor, chloroform being the proton donor. Okay, what's also interesting is if I were to think about my self-association, which would be my hydrogen bonding solubility parameter in the Hansen scheme, right, the product of these two terms would be 0. Okay, and even my chloroform term would be rather small. Okay, and with these, right, MOSCED predicts limiting activities. We could use that to get BIPs in this case for Wilson's equation. Solid lines correspond to predictions with MOSCED, and they're pretty good. Right, my pure component limit's a little off, and so I suspect there's an issue with the pure component vapor pressures. But nonetheless, we're able to capture the physics of the model using MOSCED, or physics of the system using our model MOSCED. Okay, so if you look at another example, so look at an example that exhibits a minimum boiling or homogeneous minimum boiling azeotrope of acetone methanol. Okay, so this is what would be predicted via Rayleigh's law. Circles here correspond to experimental data. Lines are my MOSCED predictions. This is my bubble line is predicted using Rayleigh's law. And so here we have positive deviations from Rayleigh's law resulting in a minimum boiling azeotrope. So now using MOSCED, we could try and get an idea of what's going on. So here again are my MOSCED parameters for methanol, or for acetone. Here are my MOSCED parameters for methanol. Okay. Remember, positive deviations from Rayleigh's law would correspond to gammas greater than 1. Okay. All right. So what do I have going on? Well, acetone's not going to do anything very special with itself. Methanol, all right, would like to associate with itself. And if I compare my MOSCED parameters for methanol to acetone, we see that methanol would rather associate with itself than with acetone. Right? So there's this preference for methanol to self-associate rather than associate with acetone, leading to positive deviations from Rayleigh's law. Okay, cool. Okay. Now that we have an idea of what MOSCED is and what makes it special, let's look at two very select applications in the limited the confines of the time I have for this talk. Okay, and the first application we're going to look at is extractive distillation. Okay, and we're going to look at monoazeotropic systems, and in the examples we'll focus in on isothermal data, isothermal VLE. We can expand this to isobaric, but that requires a little more work and is a little harder to visualize. Okay, well, a little harder to visualize in the context of MOSCED parameters, as I hope to present them in this talk. Okay. And so the general idea with azeotropic system is I have a binary system that forms an azeotrope, and I'm going to add an entrainer, a third component, to try and break the azeotrope. Okay, so get an idea of how these things work. We start with our criteria phase equilibrium, resulting from my isofugacity equations. And if I have a binary system that exhibits an azeotrope, then there exists a composition, we'll call it my azeotropic composition, for which my relative volatility is 1. Okay, where my relative volatility I can write as ratio of activity coefficients times ratio of pure component vapor pressures. Okay, where these would be my activity coefficients at that azeotropic composition. Now, to make the connection to begin to think about these things in terms of limiting activities in MOSCED, we said we're talking about monoazeotropic systems. So I have a system, at which there is a intermediate composition for which alpha is equal to 1. So what I can do is I can take advantage of intermediate value theorem. Okay? The idea being is if alpha is going to be equal to 1 at some intermediate value, well, looking at my pure component systems, again, monoazeotropic, in one pure component limit, it's going to have to be less than 1, and the other pure component limit, it's going to have to be greater than 1, right? And if that's true, then it's going to pass through 1. Okay, if I were to deal with logs, right, in one limit it's going to be negative, the other limit's going to be positive, and somewhere between it's 0. Okay, based on what those limits are, right, it's different depending on whether it's a minimum or maximum Boylan azeotrope. But if I have a minimum Boylan azeotrope, my relative volatility in the limit that x1 goes to 0 is going to be greater than 1, and that's going to be greater than my limit that x1 goes to 1, and then my relationship is just the opposite if I have a maximum Boylan azeotrope. Okay. So that's in terms of alpha. If I want to get in terms of limiting activities, I just plug in my definition of alpha. And if I do that, I find that for a minimum Boylan azeotrope, the limiting activity coefficient of component 2 and 1 is going to be greater than P1 sat over P2 sat, which is greater than 1 over limiting activity coefficient of 1 and 2. And for maximum boiling, right, the relationship is just the opposite. Okay, so this is 2 and 1. Again, we're just looking at pure binary systems, 1 and 2. And we're using the convention that component 1 is the most volatile component, so P1 sats could be greater than P2 sat. So this is greater than 1. Okay, so we get that this term then has to be positive. This is 1 over that, so it's actually an inverse relationship. So what does that mean? That means so P1 sat over P2 sat, that's going to be greater than 1. 1 over gamma 1, 2 is going to be less than P1 sat over P2 sat. So this has to be so hold on, I'm blanking. I have a moment. So I guess if I were to cover up this term, okay, if I were to write this as the inverse, then gamma 1, 2, since it's going to be less than, so it's also going to be greater than 1 for my minimum boiling case, right? My two limiting activity coefficients are going to be greater than 1. For the maximum boiling case, my two limiting activity coefficients are going to be less than 1, right? Because P1 sat over P2 sat is greater than 1. So greater than 1, less than 1. Okay? All right, so now in terms of entrainer selection, the idea being my ratio of vapor pressures is going to be constant. That's just the ratio of my two pure component vapor pressures. Okay? And then I'm going to add this third component, this entrainer. Okay? And the entrainer is going to be a non-volatile component. Okay? And the idea is we said, take for example the minimum boiling case, we said these two limiting activity coefficients are going to be positive. I want to add an entrainer to decrease the value of these two limiting activity coefficients, one or the other, so that I break the inequality. If component 1 is my least volatile component, or component 1 is my most volatile component, I want to add an entrainer so that my least volatile component becomes more comfortable in the liquid phase. Okay, and at the same time then my most volatile component will become uncomfortable and have a greater propensity for the vapor phase. Okay, and we'll look at two examples. In the maximum boiling case, essentially it's going to be the same thing. Okay, only in maximum boiling case, both of these limiting activity coefficients were negative. Right, we're going to try and change one or the other to break the inequality. Okay. And so when I add the entrainer, right, instead of 1, I could think of this as being 2 in a binary mixture of 1 plus my entrainer. Okay, 1 in a binary mixture of 2 plus my entrainer, and so on and so forth. All right, so now if I look at acetone chloroform, okay, acetone chloroform exhibits a maximum Boylan azeotrope that results from association between acetone and chloroform. Okay, in this case, acetone is my most volatile component. So what I'd like to do is I want to add an entrainer so that chloroform becomes more comfortable in the liquid phase and acetone becomes less comfortable. How I do that is I add an entrainer that chloroform would prefer to associate with as compared to acetone. So I want to add an entrainer so that chloroform would prefer to associate with the entrainer, making chloroform even more comfortable in the liquid phase, while decreasing the welcomeness for acetone, increasing its propensity for the vapor phase. A common entrainer to break this system is DMSO. So DMSO has an alpha of 0 and a beta of 26.17. So what we find is it's similar to acetone in that it has no alpha, but its beta is much greater than that of acetone. Okay. So what happens is DMSO will associate with chloroform, and that association interaction between chloroform and DMSO is going to be much stronger than the association between acetone and chloroform. So chloroform would prefer to associate with DMSO, so it's going to increase the propensity of chloroform for the liquid phase, while decreasing the affinity of acetone for the liquid phase. So if I go back to my criteria, so my maximum boiling azeotrope, what does this correspond to? Okay, so we said that component 2 is going to become more comfortable. Okay, so this value we expect to decrease. That's not what's going to break the inequality. What's going to break the inequality is we're trying to increase the value of gamma in that binary mixture. Okay, and so by adding DMSO, so we're going to make it so that the liquid phase is less attractive to acetone, right? And if you think about it, right, acetone, it's not going to do anything with DMSO. There's no specific interaction going on there. Okay. In fact, they both have no alpha, they both have a beta, and that's going to result in a positive contribution in the association term or in my residual term. And at the same time, while chloroform's still there, there's going to become less of chloroform, and chloroform would prefer to interact with DMSO than acetone. So my liquid phase is going to be less welcoming, thereby increasing the activity coefficient of acetone in that solvent. Right? And so if I had a massive database of entrainers, right, what I would be searching for is an entrainer such that the alpha of my entrainer is less than that of chloroform, while the beta of my entrainer is much greater than that of chloroform. So I'm trying to find an entrainer that acetone would really, 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 really like to associate with, more so than with acetone. Okay, cool. So if I look at a system with a minimum boiling azeotrope, so look at our example of acetone and methanol that we already talked about. So there the issue is we get a maximum boiling azeotrope, and the result is, or this results from the fact that methanol would prefer to associate with itself than to associate with acetone. Okay. So I want to flip back 2 slides. Okay. So my minimum boiling azeotrope situation, if I want to break it, okay, what I either need to do is decrease the value of gamma 2, okay, or I need to increase the value of gamma 1. Okay, well, I take it back. I want to decrease the value of gamma 2, or I want to decrease the value of gamma 1. Okay, gamma 1 being my most volatile component, gamma 2 being my least volatile component. Okay, so how we're going to break it is we want to add an entrainer that my least volatile component, again, would really like to associate with to increase its propensity for the liquid phase. So we add an entrainer that's going to cause this to decrease, breaking my equality. At the same time, well, that's the primary mechanism. At the same time, we're going to add an entrainer that component 2 would rather associate with, so that component 1 becomes less comfortable, thereby increasing this value. Okay, but the main effect is going to be to decrease gamma 2 and to break said equality. All right, so if I look at this picture, so common entrainers to break the system would be DMSO. So if I look at DMSO, we have an alpha of 0 and a beta of 26.17. So if I take TMSO and I mix it with methanol, the idea is there's going to be a propensity for methanol to associate with DMSO. We're going to get association between DMSO and methanol. They're going to like each other. Okay. At the same time, DMSO isn't going to have any sort of specific interaction with acetone. In fact, for that binary system, once again, it would increase or result in a positive contribution or positive association term in my residual contribution. Okay, so I add DMSO. DMSO is going to want to associate with methanol. Methanol is going to become more comfortable in the liquid phase. Acetone, which is my most volatile component, right, its propensity then is going to increase to be in the vapor phase, and DMSO is going to be effective in breaking the azeotrope. Another system that's been identified, or entrainer that's been identified, or environmentally friendly entrainer, is water. Okay, so you'll notice these water parameters are a little different than what I had a couple slides ago. Or what you'll see in a couple slides in my solubility enhancement. These are values that we have found are necessary for modeling VLE of aqueous systems. Okay. So the idea here is if I look at my water parameters, water is a big alpha, okay, and a smaller beta. Okay, water is a great proton donor, and what I find is water, will associate with methanol. Okay, water and methanol will associate, and it'll associate much more strongly with methanol than it will with acetone. So methanol is going to like to interact with water in my liquid phase, thereby decreasing the activity coefficient of component 2 and increasing the propensity of acetone for the vapor phase. Okay, so water will break my azeotrope because it will associate with methanol. Okay, and so using these sorts of arguments, you can come up with heuristics in terms of if I want to break a minimum or maximum boiling azeotrope. If I can identify at least the most volatile component, what does my entrainer need to look like in terms of breaking said azeotrope? Okay. The other example we'll look at, as we run out of time, is solubility enhancement. Okay, and what I mean by solubility enhancement is here's an example plot for the solubility of acetaminophen or Tylenol in a binary mixture of water and isopropanol, or isopropanol is component 1, water I call component 3, and acetone component 2. And so what I've plotted here is the mole fraction solubility of, actually my labels are off and I apologize, I just noticed this. This should be the mole fraction solubility of acetaminophen, okay, of my solid solute. And then this is the volume fraction of 2-propanol. Okay, and this B means that this is the volume fraction of my solute-free binary mixture. So this would correspond to the solubility in pure water, solubility in pure 2-propanol, and what I could picture this then as is I'm taking a binary mixture of water and 2-propanol, changing the binary composition, and measuring the solubility of acetaminophen in that binary mixture. And what we find is that there's an intermediate concentration for which my solubility goes through an extremum. Okay, and what we'd like to be able to do is, can we use MOSCED to one, explain why this extremum exists, but then also just predict whether or not we can achieve solubility enhancement for a given solute in a binary mixture. And so we'll work out the equations in the next couple slides. And so we've applied this to about 107 systems with a high success rate from this handbook of solubility data for pharmaceuticals by Joybin. Okay, so he has an entire section in the text for solubility in binary systems. Okay, so the general idea is if component 2 is my solute and component 1 and 3 are my solvent, then the mole fraction solubility is equal to the negative log activity coefficient of my binary mixture plus a log ratio of fugacities. Okay, where these fugacities are fugacity of pure solid solute and pure subliquid liquid solute. Okay, so what's important is these are properties of my pure solute. If I assume that only solute-solvent interactions are important, or if I just general assume that my concentration is relatively small, then I can replace my activity coefficient with my limiting activity. Okay, so I'm going to say that log x2 is equal to log gamma 2, my negative log limiting activity coefficient, plus this log ratio of fugacities. Okay, so again, this is a pure component descriptor, or a property of my pure component solute. So if we expect log x2 to go through a maximum, then it must be that log gamma 2 at infinite dilution goes through a minimum. Okay, so MOSCED we can use to predict limiting activity coefficients. So we want to turn this into using MOSCED to identify the ability of a solute to exhibit a minimum in log gamma 2 at infinite dilution in a binary mixture. Okay, so MOSCED as we've written it so far is applicable for binary mixtures, so solute in a pure component solvent. So how we extend it to binary mixtures is we compute our MOSCED parameters for our solvent as volume fraction average of the pure component solute parameters. So remember, component 1 and 3 are my solvent. So to given volume fraction, I can calculate the volume average of those two solvent descriptors to get a descriptor for my solvent. Okay, so now we haven't tested this out extensively, but at least for this application, this volume average mixing rule seems to work pretty well. Okay, it was suggested in the original 1984 MOSCED paper with the skepticism that this is how it would work in regular solution theory, but we're not so sure about MOSCED itself. Okay, and so in doing this, what we can do is this will allow us to calculate limiting activity coefficients of my solute in a binary mixture of this composition. Okay, and this is useful because we're trying to calculate or determine if log gamma 2 at infinite dilution can go through a minimum. And so now we could rigorously do this. We could just vary phi and calculate the corresponding limiting activity coefficient of my solute at each of those compositions and see if it goes through a minimum. Or we could just as well calculate limiting activity coefficients for component 1 and 2, 1 and 3, 1 and 2, 2 and 3, 2 and 3, 3 and 2, if I got all my binary components right. Use that to fit bips of excess Gibbs free energy model, and then rigorously calculate gamma infinite dilution as a function of composition and see if it goes through an extremum. We could do that. But one of the beauties of MOSCED is it's a solubility parameter-based method. Right? And the beauty of solubility parameter-based methods is our ability to use them for intuitive solvent selection and formulation. Okay? And so what we did is we said, okay, we want to minimize log gamma 2 in infinite dilution. And so we're going to make a few assumptions. So the assumption we're going to make is we're going to assume that the important feature that accounts for these minimums is association interactions. Right? And again, we're trying to minimize log gamma 2 to infinite dilution. Okay? So, finding a minimum can mean a lot of things, but if I just think in terms of, gamma 2, we said the combinatorial term could be negative. In terms of the residual term, okay, it can be negative. The only way to get negative contributions is via my association term. Okay, so if I just assume that the association term must be, what's causing this effect, let's just consider my association term and try and minimize it. And to simplify the calculations, let's ignore for now our asymmetry term and just look at this difference in alphas and betas term. Okay, and so if I'm looking for whether or not this term then goes through a minimum, okay, the test would be, well, first let me compute the second derivative and let me see if the second derivative is greater than 0 to see if it's concave up. And then, if it is concave up, I can find the minimum by computing the first derivative and looking for where. So, if I compute the second derivative, this is my check to see if this term is greater than 0. Okay, and so then if it is concave up, I can then check to see if it goes through a minimum by searching or computing the first derivative and looking for the composition where the first derivative is equal to 0. Okay, and so from the second derivative test, we already get our first criteria for how to choose solvents. Okay, in order for this term to be greater than 0, it must be that component 1 and component 2 do not associate with each other. Okay, so it has to be that either alpha 1 is greater than alpha 3 and beta 1 is greater than beta 3, or alpha 3 is greater than alpha 1 and beta 3 is greater than beta 1. In either scenario, component 1 and 2 have no propensity to associate with each other. Okay, cool. So then if that criteria is satisfied, I have two solvents that don't want to associate with each other that I'm mixing together. Then in my first derivative test, if I solve for my concentration, I get this. Okay, and so if I calculate phi and I find that phi is a value between 0 and 1, then my system's going to exhibit an extremum, or it's going to exhibit a minimum, and that minimum will happen at that value of phi. Okay, and in order for that to happen, right, we come up with some heuristics then in terms of what the solubility parameters of component 2 must look like relative to component 1 and 3. Right. All right, and so the general idea is going to be is if I choose a binary mixture, I want those two solvents not to associate with each other, and I want to find a solute for which those solubility parameters of my solvents, either bracket alpha or bracket beta of my solute. The general idea then being is, as I change the volume fraction or concentration of my solvent, I'm looking for that sweet spot so that I would change the solubility parameters of my solvent just to the right degree so that there becomes a propensity for my solvent to associate with my solute. Okay, and so if I look at this example of 2-propanol and water, okay, so here solubility parameters for 2-propanol, solubility parameters for water. Okay, so in terms of my first criteria, right, it passes. So 2-propanol and water have no desire to associate with each other. Okay, and even if I were to use our updated solubility parameters, we get exactly the same result. Right, so water and 2-propanol don't want to associate with each other. Water would prefer to associate with itself. Now, if I look at acetaminophen, here's my solubility parameters for acetaminophen. Okay. And so what happens, okay, is water would prefer to associate with itself. As I add 2-propanol to my system of water, okay, my solubility parameters are going to change, right? So my solubility parameters are essentially going to decrease from these values in my pure water limit to these values in my pure isopropanol limit. So as I decrease these values, they're decreasing at different rates. Remember, alpha 3 is much greater than alpha 1, beta 3 is much greater than beta 1, or beta 3 is greater than beta 1, but not to the same extent as alpha. So as I add isopropanol to my water-rich phase, okay, what we are essentially what we want to happen is we want to decrease the value of alpha of my solvent, okay, just enough so that there becomes let me try and make sure I get this right. So we're going to decrease the value of alpha at a faster rate than beta. What we're trying to look for is that sweet volume fraction so that there becomes a propensity for my solvent to associate with my solute. Okay, so right now, if I were just to look at water, water would rather associate with itself. Okay, so in order to get water to associate with my solute, what I either need to happen is to have my solvent have an alpha value greater than my solute, but then beta of my solute to be greater than beta of my solvent, or vice versa. Okay, and so that's exactly what we're going to get to happen. So alpha is going to decrease, right? And so our MOSCED prediction, this happens at a mole fraction about 0.7. Alpha is going to decrease, but it's still going to be greater than alpha of my solute. We're going to decrease beta of my beta of my mean solvent, so that we get to the sweet spot so that my solvent is going to want to associate with my solute. Okay, and using these MOSCED expressions, we obtain a mole fraction or volume fraction of about 0.7. So experimentally, this happens just above 0.8 volume fractions. So numerically, the values are slightly different, but using MOSCED, we're able to predict the presence of an extremum using these very simple expressions that aren't too far off from experimental values. Okay, and if we were to do rigorous predictions, the results don't change a huge amount. But then not only that, just using this, we can gain some insight in terms of what's going on. How does this extremum happen? And we've actually looked at this binary system using simulation, and we actually observe the same phenomena, right? And then if you think about just pure water, right? When I have pure water, it's going to want to associate with itself. As I add more and more isopropanol, right, to my system, as I decrease the concentration of water, and I get this homogeneous system, right, what's going to happen is I end up essentially isolating these water molecules. They're then going to want to associate with my solute. All right, so there's some other standard applications that we've looked at that I don't have time to talk about. We've been able to extend MOSCED to polymers, right? So we can use the residual contribution to calculate chi, and due to this residual term, we can actually calculate negative chi's, which is pretty exciting. We've now parameterized MOSCED for ionic liquids. We have parameters for over 120 ionic liquids. Right? And what we found to be special about ionic liquids is they have a very large beta, a beta much larger than any of the conventional solvents in the original database. Okay? And it says beta, which makes ionic liquids so attractive for breaking azeotropes. We could do standard phase equilibrium calculations, SLE, LLE, and VLE. We've computed solvation-free energies compared to the free-solve database, and MOSCED performs extremely well, better than those simulation results. We calculate Henry's constants. We've shown how we can calculate partition and distribution coefficients and selectivity. And we've even started to do some work showing how you can use MOSCED to correlate pure component descriptors, much like the folks with LSER or Abraham parameters have demonstrated that they can. And in theory, if these MOSCED parameters are physical descriptors, right, you should be able to use them in QSAR-based methods. All right. So the last thing I want to quickly mention before we wrap up, as I said, kind of the state of the art with this 2005 paper is, Eckert and co-workers were able to regress parameters for 130 organic solvents. Okay, and so MOSCED is great; it works fantastically well, but I see this as being one of the main limitations, right? Especially for design applications. I'm limited to working with only these 130 organic solvents and water, and so a lot of the papers that I showed in the initial citation list is we've focused on ways to try and expand the MOSCED database, to try and turn MOSCED into a predictive tool similar to UNIFAC and similar methods. And so what we found is, in terms of expanding MOSCED, the key is the relationship between limiting activity coefficient and solvation-free energy. Right? Solvation-free energy is key because there are plenty of predictive methods out there to get solvation-free energy. We can calculate solvation-free energies using molecular simulation, electronic structure calculations, and continuum solvents, and we'll show how we can use LSER methods also. Okay, so the first one I mentioned is LSER methods. So LSER methods are attractive because, mostly due to Ackery and Abraham, there are a massive number of published LSER parameters. LSER is great for correlating parameters or properties in a given solvent. So if I have a database of 1,000 solvation-free energies in methanol, and I have LSER parameters for all those solutes, LSER is fantastic at correlating solvation-free energy in that solvent. Okay, but it's only good, or I say it's restricted for correlating in a particular solvent. The advantage that MOSCED has is for making predictions of any binary combination. And so what we've done is we've tried to leverage the strength of LSER to predict MOSCED parameters. And in theory, our LSER parameters are related to the same physical quantities as MOSCED. E and V are related to dispersion interactions. S is related to polar. A and B are related to proton donating and accepting ability. Right? So there should be some relationship between the two. We tried for a year to try and find a direct mapping with no such luck. What we found that worked is we take advantage of what LSER is good for, and we have developed correlations for about 90 solvents. And then once we have these correlations for correlating solvation-free energies, I have a new component I'd like to parameterize. If I have its LSER parameters, I could plug it into these 90 correlations, get a set of 90 reference solvation-free energies, which I can then use to fit MOSCED parameters. All right? And this has worked extremely well. In a similar token, we've also used molecular simulation and electronic structure calculations, namely the SMD, SM8, and SM12 continuum solvation models, to generate reference solvation-free energies, which we've used to train MOSCED. Okay, solvation-free energies and simulations are nice. If you can draw the molecule, you can make predictions. Timescale these electronic structure calculations is much shorter than the simulations, but the accuracy is not quite as good as LSER. We've also cooked up group contribution methods. So the first one was based on the GC plus method of Ghani, based on the 130 MOSCED parameters. We've gotten a lot of emails, though, of, hey, can you predict MOSCED parameters for this compound? And so, recently we've tried to develop a very simplified group contribution method just using daylight smarts descriptors that one can use to predict MOSCED parameters, and have that implemented in OpenBabel to really facilitate its use. But we have GC methods to directly calculate MOSCED parameters and LSER parameters as well. Okay, and the very last example, I'm well over the original 30 minutes I had in AIChE, but nonetheless. Okay, so just to kind of demonstrate, so here's isobaric VLE for a system of ethane diol and naphthalene, where ethane diol and naphthalene, so there's no MOSCED parameters for ethane diol. There are MOSCED parameters for naphthalene fit to solubility data, but we ignored them since we're predicting VLE. And so what we have shown here is we used our Ghani-based GC method to predict MOSCED parameters for ethane diol and naphthalene, and we also use solvation-free energies in the SMD and SM8 continuum solvation models. So we predict our MOSCED parameters for ethane diol and naphthalene, and then once we have those, we use that to predict BIPs using limiting activity coefficients, to train NRTL to predict VLE. Okay, and what we find is that our predictions aren't all that bad. Right? In all cases, we're able to predict the location of our azeotrope. Okay, in this case, location is pretty spot on with the experiment. It's just my temperatures are slightly off. Okay, and on the right plot, so in this left one I compared to mod UNIFAC. The right plot, it's the same set of predictions that we made, but instead of mod UNIFAC, I include the reference NRTL. So the data from ChemCAD using the NRTL parameters that they provide for this binary system. And the reason for showing that is, mod UNIFAC, we see some deviations between our best predictions with our GC method and SMD. But when I use the ChemCAD reference data, those are a much greater agreement with our predicted values. Okay, and so to wrap things up, again, we've published a slew of papers on this. These papers are mostly related to predicting MOSCED parameters using electronic structure calculations, molecular simulation and group contribution methods, and also some of our basic work in terms of predicting phase equilibria using MOSCED. The entrainer selection, solubility enhancement, and LSER parameters, those are papers that, and even the ionic liquids and polymers and some of those applications, those are papers that we're currently writing up and should hopefully be submitted soon. If you have any questions or want any help about using MOSCED, right, you can send me an email here. I'd be more than happy to help you. Okay, and with that, I'll thank all of my funding sources for all these projects. And I should note I've mostly worked on all these projects with undergraduate students. It's me and a group of undergrads for the most part. I have had one graduate student, Proctor Dockel, which is carried out a lot of this work in the last 2 years. But even that involved lots of undergrads. So again, you can email me with any questions, comments, or if you would like any help. And this screencast is going to be posted to my YouTube channel here. If you want any other tutorials about MOSCED or informational videos, send me an email, and I will go ahead and make those when appropriate. Okay. So thank you, and we'll see you later.